Well, welcome back. This is pre-section 6.1 video. Section 6.1 is called integration by parts. Now, what you've learned in section 5.5 is probably the most important technique of integration, which is called U substitution. You're learning how to take hard problems and with the appropriate U substitution turn them into simple problems. Well, in chapter 6 and including section 6.1, we're going to now be looking at more in-depth formulas for particular types of problems. The first formula is called integration by parts. It is a formula which is what I call an offsetting integral. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. Now, here's the whole idea. You're given a problem on an integral, and you're going to look at it as two parts, a u part and a dv part. You're going to set it up where you're going to figure out what u is. You're going to take the dv and figure out what v is. You're going to subtract the integral of the v part minus whatever u was. You'll take the derivative of it, and that'll be du. The idea behind this is this. Here's a formula. When u substitution does not work, very important, if u substitution doesn't work and it's a product, the integral of u dv is equal to uv minus the integral of v du. You'll plug it into this formula, and the goal is if you can't integrate this guy, by plugging into this formula, you should be able to integrate this guy and get your answer for the integral. So it's not a formula for getting the answer, it's a formula for, well, if I can't integrate this, I apply the formula and I'll integrate this. But most important, u substitution didn't work first. Always try u substitution first. And as I just mentioned, where does this formula for integration by parts come from? It's derived from the product rule. So if you look at this thing, there is actually some of that product rule and things like that. And if you think about u substitution, it actually is derived from the chain rule. But the product rule, this integral of u dv equals uv minus the integral of v du, is actually the product rule written in code. So if you can't integrate this guy, apply the formula and integrate this. So let's just try some problems. Here's my first problem right here. The integral of 3x e to the 6x dx. All right. Now, u substitution doesn't work here. What I mean by u substitution doesn't work is this. If I was going to do u substitution, I would let u equal to exponent on e's, 6x. That means du equals 6 dx. And when I substitute over, it'll be e to the u du. The problem is there's an extra x left over. When you're doing u substitution, you should substitute it. All the x variables go away. You should get nothing but constants and u's. This one, if I did the appropriate u substitution, there's an extra x to kind of shove it in the problem. So u substitution doesn't work. And once I decide u substitution doesn't work, and I view the problem as a product, this is 3x times e to the 6x dx, I can apply integration by parts formula. The integral of u dv equals uv minus the integral of v du. And every time I actually decide I'm going to use integration by parts, I always write down the formula I have memorized. Here's the deal. On this particular problem, I'm going to let u equal to 3x because when letting u equal to 3x, then I have to actually find du for the formula. The derivative of 3x is 3 dx. The rest of it is dv would be equal to e to the 6x dx. But this is d, standing for derivative. So I need to get v back again to be able to plug into my formula. And to actually get v back from dv, I actually have to integrate this e to the 6x dx. I want to remind you of some of your basic rules you have memorized from section 5.5, and that's that e to the kx dx formula. The integral of e to the kx dx is 1 over k. In this case, it'll be 1 over 6 e to the 6x. That's one of those fast tricks of integration that's going to come in very handy here. So, when I want to let u equal to, now you had two parts to let u equal to. You could have let u equal to 3x or let u equal to e to the 6x. But here's the deal. You should let u equal to the part you want to get rid of, and you get rid of things through the derivative. That x was causing me all the problem, and that's why u substitution didn't work. So I would let u equal to that part, 3x, and then taking the derivative, I get 3 dx. Now, watch this. I'm going to apply my formula. This is the integral of u dv. That'll be equal to u times v minus the integral of v du. I'm going to substitute. Unlike u substitution, we don't manipulate constants. So we just plug it in exactly where it's at. Here's u. What was u equal to? It was 3x. Times v. What was v equal to? 1/6 e to the 6x. Minus the integral of what was v? That was that 1/6 e to the 6x. And then times du, and du is 3 dx. Literal substitution, but unlike u substitution, you don't move the constant to the other side. You just literally plug it in to your formula. So, here we go. Clean it up before you integrate it. So this becomes 3x times 1/6 e to the 6x. Well, 3 divided by 6 is a half, so this is 1/2 x e to the 6x minus 3 times a 6 is a half. In terms of an integral, that goes out front. The integral of e to the 6x dx. So I clean this guy up by pulling my constants out front. Now the whole purpose of integration by parts is if you can't integrate this guy, because u substitution doesn't work and it looks like a product, I apply this formula and then I have to integrate this part. But this is just like we did before. This is the classic integral e to the 6x dx, or e to the kx dx. The integral e to the kx dx is 1 over k e to the kx, so it's kind of a fast u substitution in my head. So this is 1/2 x e to the 6x minus 1/2, and the integral e to the 6x dx is 1/6 e to the 6x. There's no bounds on this stuff, so plus c. Now I'm going to clean it up and get my answer. This is equal to 1/2 x e to the 6x minus 1/12 e to the 6x plus c. And that's one way the answer could look. I could also factor out something that's in common, or in getting to his multiple choice answers, I could factor out maybe a constant, maybe take out the 1/2 and the e to the 6x, and if I did that, that would leave me with an x minus 1/6 plus c. There's lots of different ways you can actually do the algebra, manipulating the answer and stuff. Honestly, we're happy either which way, but remember this trick if you're looking for multiple choice answers on your pre-quiz and stuff. Now, if you compare that question to this question here, it's the integral from 0 to 3 of 3x e to the 6x dx. You'll notice it's the exact same problem as up here, except I have bounds. So, just want to remind you, I have to integrate this guy, but all the work on integrating was up here. I got this answer right here. But because I have bounds to be able to do this problem, I'm going to take my solution, and I like this answer better. This will be 1/2 x e to the 6x minus 1/12 e to the 6x. Instead of putting the plus c, I have bounds, so now I'll go from 0 to 1, one extra hoop to jump through, and use the second part of the fundamental theorem of calculus about plug-in top minus plug-in bottom. This would be 1/2 times 1 e to the 6 times 1 minus 1/12, excuse me, e to the 6 times 1 minus plug-in top minus plug-in bottom. And be careful when you plug in 0. This would be 1/2 times 0 times e to the 6 times 0 minus 1/2 e to the 6 times 0. But 6 times 0 is 0, and e to the 0 makes it 1. If it was 0 times a half is 0 times e to whatever, still 0, so that's 0. So you can clean this up to get 1/2 e to the 6th minus 1/12 e to the 6th minus e to the 0 goes to 1. That part's 0, so that's minus negative a half. And so you end up getting your answer. A common denominator here would be multiply the top and bottom by 6 This will give me 6 over 12 e to the 6 minus 1 over 12 e to the 6. Minus a minus is a plus 1/2. So I end up getting my final solution when I evaluate the integral is, let's see, 6/12 minus 1/12, combining like terms, would be 5/12 e to the 6 plus 1/2. And there is my numerical value. So, when you're integrating, the key to it is, when you got bounds, you still have to integrate. So all this work was to integrate this guy. And again, because u substitution doesn't work and it looked like a product, I let u equal to 3x. That makes du equals 3 dx. Let dv be e to the 6x dx. And you always make sure you let dv be something you can integrate. When I integrate it, I get 1/6 e to the 6x. I apply my formula. Integral of u dv is u times v minus the integral of v du. I clean them up, and then I integrate the second integral, and then clean up my answer. And when I got bounds, I go back and plug in top minus plug in bottom. So let's do another example. Well, here's another one. The integral of 2x cosine of 5x. Now, again, first thing I should always do is try u substitution. But if I was going to do this kind of problem with u substitution, I would let u equal to the angle on the trig function. I would let u equal to 5x, which means du equals 5 dx. That's great. The dx gets replaced with 1/5 du. That's cosine u. And I still got this 2x out front that never got substituted. And remember, with u substitution, everything should be substituted. So u substitution doesn't work. And again, it's a product. It's the integral of 2x times cosine of 5x. So again, I'm going to use my integration by parts formula. Integral u dv equals uv minus the integral of v du. And I'm going to let u equal to, well, I got two options. I can let u equal to 2x or let u equal to the cosine of 5x. I always want to let u equal to the part that when I take its derivative, it goes away. And my problem is this 2x. So I'm going to let u equal to 2x. And therefore the dv has to be the other part, which would have been the cosine of 5x dx, the rest of it. Now, another reason why I did not let u equal the cosine of 5x, because when I take its derivative of cosine of 5x is going to be negative sine of 5x times 5. It doesn't go away, it just changes from cosine to sine. It's just changing the trig form. I want the terms to eliminate to make it a little bit smaller. Again, think about that u substitution, and what was giving you the problem is traditionally what you let u equal to, right? But your teacher will go into great details about all the different types of techniques and when you should let u equal to which types of problems. So, but once you decide what u is in dv, then you have to do du to set up your chart. U equals 2x, then derivative of 2x is 2 dx. dv is the cosine of 5x dx, and again, this is that I need to integrate to get v back again. This is the integral of the famous cosine of kx dx formula. Integral of cosine of kx dx is 1 over k sine of kx plus c. So k is 5, so that'll be 1 over 5 sine of 5x. No plus c's on this stuff until we get our final answer. But these are the parts that I'm going to substitute in for. So this integral of 2x cosine of 5x dx is going to be equal to u times v. That'll be 2x times 1/5 sine of 5x minus the integral of v, which is 1/5 sine of 5x, and then plugging in du, and du is 2 dx. So literally you plug into them. You don't manipulate constants, you literally just plug them in and then clean it up. Well, 2 times 1/5 is like 2/5. That'll be 2/5 x sine 5x minus, pulling my constant out front, the constants are 1/5 times 2, that would be another 2/5. The integral of what's left, the sine of 5x dx. Now, to do this problem, all I've got to do now, this offsetting integration of integration by parts, is integrate this guy. So this would be 2/5 x sine of 5x minus 2/5. And this type of integral, there's lots of different techniques to integrate. You could be a simple formula. You could do u substitution. Sometimes you may end up having to integrate this guy by using integration by parts again. But this is, again, a formula that you should have memorized by this point. This is the famous integral of the sine of kx dx, quick integration formula, which would be times the integral of sine is negative cosine, so this will be negative 1/5 cosine of 5x. And then at the end of the problem, one big old plus c. And again, cleaning this up, my final solution would be 2/5 x sine of 5x. A negative times a negative is a positive. 2/25 cosine of 5x plus c. So you'll notice you do a lot of algebra cleanup when you're doing these kind of problems and stuff. Well, let's do one more for good practice and making sure we're doing very similar problems that are going to be on your quiz to follow the pattern here. I've got this integral of natural log of x over x cubed dx. Again, u substitution is clearly not going to work here because whatever I let u equal to, like natural log of x du, 1 over x is not in the problem. I got 1 over x cubed. Extra x is left over. The other deal is this. You'll notice that the way I've written this one, it is not a product. Integration by parts is when u substitution doesn't work and it's got to be a product. So the first thing I'm going to do is clean this guy up. This will be integral of x to the negative 3 times the natural log of x dx. Now it looks like the formula that I'm going to use, which is that integral of u dv equals uv minus the integral of v du, integration by parts formula. The trick is, what are you going to let u equal to? What are you going to let dv be equal to? Now, in terms of integrating this stuff, the other trick is I typically want to let u equal to the part I want to get rid of, and you get rid of things through the derivative. What's causing the problem in this one? Is it the x to the negative 3 or is it the natural log of x? Well, in this particular problem, I would let u equal to the natural log of x. The reason why is that when I take its derivative, it goes away. Derivative of natural log of x, think calculus 1. Derivative of natural log of x is 1 over x dx. And dv would be the x to the negative 3 dx. Now you remember they could be either one. They sometimes mix them up, but in terms of being front and backs and stuff. So dv would be this guy. So you integrate to get v back again. So the integral of x to the negative 3 dx is x to the negative 2 over, add 1 over add 1, negative 2. No plus c's on this one. And the other reason why I let u equal natural log of x is if I let dv be the natural log of x, what's the integral of that guy? No, it's not 1 over x. The integral is going to require some more formulas and stuff. We actually haven't integrated natural log of x. We've only taken its derivative. So now applying our formula here, so writing it down here, this integral would be u times v. U would be natural log of x times v, which would be x to the negative 2 over negative 2. We'll clean them up later. Minus the integral of v, x to the negative 2 over negative 2, times du, which is 1 over x dx. Literal, plug it into my formula. But you'll want to clean him up. And you want to clean this guy up so you can integrate him. You want to clean this guy up just to make him look good. So this would be equal to negative exponents go on the bottom. This would be negative 1/2 times the natural log of x over x squared. A negative is a positive, plus, and I'm pulling the 2 on the bottom out front, makes it 1/2 the integral. But here's something very important. Always clean it up before you integrate it. The old John's Fun Rule Calculus. Clean it up first. X to the negative 2 divided by x. When you divide, you subtract exponents. This is understood to be x to the first. So x to the negative 2 divided by x, that'll be negative 2 minus 1. That'll be x to the negative 3 dx. Now, all you've got to do is integrate this guy. Integral of x to the negative 3 is add 1 over add 1, x to the negative 2 over negative 2. You still have your 1/2 out front. And you got this negative 1/2, the natural log of x over x squared holding over. No bounds, plus c, so there's my solution. But of course, I always like to clean these guys up for my final answer. So my answer is going to be negative 1/2 times the natural log of x over x squared minus 1/4. And I got a fourth from 2 times 2 is 4. That negative times a positive is where that minus came from. X to negative 2 goes on the bottom times 1 over x squared plus c. And there's my final answer. Okay, you could also write this as negative 1/2 the natural log of x over x squared minus 1 over 4x squared if you want to put your two fractions together plus c. And there's lots of ways to clean it up if you want to factor something out or whatever, but this is the algebra behind this stuff. So not too bad of a formula, but it has its potential. Now we're just getting started scratching the surface on the potential of this particular formula. Again, the world's worst ones is when you use this integration by parts, integral of u dv equals uv minus integral of v du. The goal is to integrate this guy. Sometimes you have to do, it's a formula, sometimes it'll be u substitution, sometimes it'll be more integration by parts. Your professors will go into great detail on the power of the integration by part formula. I hope this has been helpful, and I'll see you guys on the next video.